You know that big, colorful chart from chemistry class, right? The periodic table? Well, what if I told you it's got a secret, a really weird one, a kind of hidden twinship that breaks one of the biggest rules we thought we knew? Let's dive in and solve this thing. So what we're looking for are these, well, chemical doppelgangers. You've got these pairs of elements that, if you just look at where they are on the table, they should have nothing in common, but somehow they act almost exactly alike. How on earth is that even possible? And that brings us to the big question, right? The core puzzle we're trying to solve here. Why do some elements that are diagonal from each other act like chemical twins? They're not even in the same family, not in the same column. Something's up, and we're gonna figure it out. Okay, so let's back up a sec. The number one rule of the periodic table, the one they drill into you in Chem 101, is that elements in the same column, the same group, they share properties. It's why all the alkali metals are in group 1, right? It's the foundation of the whole thing. But this weird diagonal thing we're seeing, it just throws a giant wrench into all of that. And here they are, our culprits, the odd couples. You've got lithium and magnesium, beryllium and aluminum, and boron and silicon. Look at them. They're not in the same groups at all, but there's this strange diagonal link between them. So what is going on here? What's the secret? All right, time to put on our detective hats. To crack this case, we have to go back to the basics. We need to understand the fundamental rules that govern the entire table. These are going to be the clues that lead us to the answer. So our first major clue is something called the atomic radius. You can just think of it as an atom's size, its personal bubble. It's the distance from the very center of the atom, the nucleus, out to the absolute edge of its electron cloud. And believe me, this size is a huge deal. Now, this is where things get a little weird, a bit counterintuitive. As you move from left to right across the table, you'd think atoms get bigger, right? Nope, they actually get smaller. Why? Because you're adding more protons to the nucleus, and that stronger positive charge pulls the whole electron cloud in tighter. But if you move down a column, they do get bigger. That's because you're adding whole new layers of electrons, kind of like adding another layer to an onion. And you can see it right here. This isn't just theory. On one side, you have the rules spelled out. Smaller to the right, bigger as you go down. And on the other, you can actually see the atoms themselves. Look how tiny something like fluorine is compared to lithium in the same row. And then look how potassium just dwarfs lithium from the row below. It totally works. Okay, on to clue number 2, electronegativity. This sounds complicated, but it's not, I promise. Just think of it as an atom's electron greed. It's basically a measure of how badly an atom wants to pull electrons towards itself when it's in a chemical bond. And you've probably already guessed it, this is directly connected to an atom's size.
And it really all just boils down to how close everything is. If an atom is small, its outer electrons are way closer to that positively charged nucleus. So the pull is just stronger. It's that simple. So the main thing you gotta remember is this. Smaller atoms are greedier atoms. They have higher electronegativity.
Okay, let's take a beat. We've got our clues. We know about atomic size. And we know about this electron greed, electronegativity. We have everything we need. Now, let's put it all together. This is the aha moment. So let's break it down piece by piece. Imagine you take just one step to the right on the periodic table. What happens? The atom gets smaller, and its electron greed, that electronegativity, it goes up. Simple enough? But what if you take one step down the table? Well, you get the complete opposite effect. The atom gets bigger, right? And that weakens the pull from the nucleus, so it becomes less electronegative. You see, we've got two totally opposing forces at play here. So what happens when you do both at the exact same time? What happens when you move diagonally, one step right and one step down? Well, these two opposite effects, one making the atom smaller and greedy, the other making it bigger and less greedy, they almost perfectly cancel each other out. And the result? Their properties end up being shockingly similar. How cool is that? Okay, so that's the theory. It's a really neat idea, this balancing act of forces, but does it actually hold up when the rubber meets the road? Let's check out a real-world example and see the proof for ourselves. Let's go back to our first pair of doppelgangers, lithium from group 1 and magnesium from group 2. Now, according to the textbook rules, these two should be pretty different. But because of this diagonal thing, their actual chemistry is just, well, it's spookily similar. And the evidence is just undeniable. Get this. Lithium is the only metal in its entire group that forms a stable nitride compound. And guess who else does? Magnesium. They both form these things called covalent organometallic compounds, which is super different from their group mates who form really reactive ionic ones. Even their chlorides act the same way. These aren't just little coincidences. This stuff completely flies in the face of the standard column-based rules.
So, there you have it. Mystery solved. We figured out the secret of the chemical twins. But what does this actually tell us about the periodic table itself? Let's zoom out and look at the big picture here.
All right, so let's wrap up the key takeaways. First, we know that things like atomic size and electronegativity, they follow predictable patterns. That's a given. Second, moving across the table and moving down the table have opposite effects on those patterns. Third, and this is the big one, these opposing forces pretty much cancel out on the diagonal, which explains why they're so similar. And what does that all mean? It means the periodic table isn't just some static chart on a wall. It's a dynamic map full of competing forces and hidden relationships.
You know, this whole diagonal relationship, it's way more than just a neat bit of trivia you can use to impress your friends. It's a perfect, beautiful example of the deep, subtle, and honestly predictive power that's woven into the very fabric of the periodic table.
Think about it. This whole diagonal thing was a surprise, and it was hiding in plain sight the entire time. It really makes you wonder, doesn't it? What other hidden patterns, what other secret rules and connections are just waiting to be discovered in this incredible map of the universe? What else is out there that we haven't seen yet?